Hi everyone. So in the next two lectures, we're going to be looking at S-block elements and some of the compounds that these form. And as it's sort of one big topic, I'll be keeping all the videos in one playlist on YouTube or one folder on Blackboard for both of the lectures. And it'll consist of about 7 or 8 parts. And in this first part, we're just going to look at an overview of the metals of group 1 and 2, compare them a bit and look at some of their properties. So the S-block elements are on the left-hand side. There's group 1 and 2. And they're called the S-block elements because the valence electrons are in the S shell. So in group 1, it's NS1 electron configuration. And in group 2, the electron configuration is NS2. Group 1 can also be called the alkali metals. And this is because the metals react with water to form basic compounds. And group 2 are called the alkaline earth metals. And this is because the oxides of the metals, and this is where earth comes into it, it's like an old-fashioned way of talking about the oxides. So the oxides of these metals are alkaline. So let's start by taking a brief look at the group 1 metals. Here you can see pictures of all of them. Francium on the right-hand side is, not so much is known about it. We won't be talking about that. And this is actually one of the scarcest naturally occurring elements. Very little of it is in existence and very little is known about it. But in contrast to that, sodium and potassium are among the top 10 most abundant elements in the Earth's crust, and some of the most used elements actually in society. So they vary a lot. And one important thing about all of these is that they're very reactive. So they react with water and they react with air. So they have to be kept in oil to stop them reacting. And with this YouTube link, I've got a nice video to a Royal Society of Chemistry lecture where someone shows the reactions of the first 5 of these with water. So if you want some explosions and fire, you can find them there. So things like the melting point, boiling point, and enthalpy change of atomization of the group 1 alkali metals are all low compared to other metallic elements. And this is because only one electron is contributed to the electron pool. And what this means is there's weak metallic bonding present. So if you remember when we looked at solid structures, metallic elements form these metallic structures. So you've got the cations with a pool of electrons flowing between these cations and holding it all together. And these cations each only supply one electron to this electron pool. So the forces between these are not so strong, and that means there's weak metallic bonding and leads to things like low melting point, low boiling point. As an example, the melting point of cesium is barely above room temperature. If you hold it in your hand long enough, if it's a hot day in the lab, cesium can melt. I think it's around 28-30 degrees. Lithium is slightly higher. It's about 180 degrees. But comparing that to other metals like iron and stuff, I mean, if you can melt it in your kitchen oven, it's not a very high melting point for a metal. And the final thing that's characteristic about them all is that they've got quite a low density. And this is for 2 reasons. One of them is the large atomic radius. So if you remember back to the first video, we said that the atomic radius decreases as we go across a period. And since the group 1, that's at the beginning of the period, these have the largest atomic radius of the period, so that contributes to the low density. Also, the solid structure that they adopt, this body-centered cubic structure. If you remember back to the second video, body-centered cubic wasn't one of the close packing structures, so it's quite open, there's quite a lot of space in there, and that also contributes to the low density. Here are the group 2 metals. These are all solids at room temperature. They're less reactive than group 1. They won't spontaneously ignite with water or anything. And although they will form like a surface oxide usually if exposed to air, and this actually passivates them, we call it. It makes them less reactive even than you'd expect. They have higher melting points, boiling points, and enthalpy changes of atomization than group 1. And this is because they've got stronger metallic bonding. So instead of each metal cation giving 1 electron to this electron pool, each of them gives 2 delocalized electrons. So this leads to stronger attractive forces in the metal lattice, stronger metallic bonding, and therefore higher melting points, higher boiling points. So the chemistry of group 1 is dominated by its +1 oxidation state. So it's easily oxidized into M+ ions. This is because it's got a low first ionization enthalpy. As I was saying, they're very reactive. If you watch the video, if you put any of these metals in water, they will fizz, bang, and catch on fire. And each of the metals has a distinctive visible spectrum, which you can see with the flame tests. So if you take some of the metal and put it in a Bunsen burner, the flame will change colour, and the colour is distinct, indicative of which metal it is. And things like sodium's a very bright one, so even impurities of sodium will mask the other colours. They're used to give street lamps their colour. Group 2, they're dominated by the +2 oxidation state. So I'll go a bit further into oxidation states, but especially on the help sheet it's mentioned as well. There are some rules for calculating oxidation states, and two of the rules in fact, are that in a compound, group 1 metals will almost 100% of the time be in the +1 oxidation state, and the other rule is that group 2 metals will almost 100% of the time be in the +2 oxidation state. And this is because they very easily form M2+ ions. They've got a very low first and second ionization enthalpy. That's why they form 2+. And because of this 2+ charge, they have high lattice enthalpies for the salts. So this is something we looked at as well in the second lecture when we were looking at solid structures. Because the cations are 2+, and they'll be offset by 2 negative charges or a 2-. It's much stronger interaction than, say, a cation with 1+, like the group 1s. So they've got much higher lattice enthalpies of the group 2 salts than the group 1 salts. Beryllium's an exception. Beryllium, is an exception. Can't speak. And this mainly forms covalent compounds. This has to do with its electronegativity being somewhat higher than the rest of group 2, and especially group 1 as well. It's something we saw with the hydrogen compounds, and I'll talk about that in a separate lecture at the end. Again, with the exception of beryllium, group 2 have quite distinctive colours in the flame tests, and there are some examples down here. Magnesium is less of a colour. You probably won't be able to see this lovely purple, but if you did it in the lab, I think this is like a very optimized photo. It's just incredibly bright white. So let's take a look at how some of these group 1 and 2 metals are prepared. It's important to know that none of these group 1 and 2 metals, because they're so reactive, even the group 2 that I said weren't as reactive, they're still quite reactive. Because they're so reactive, you won't find them just in metal form on Earth. Like, you won't just find a pile of sodium metal. They're always in ionic compounds. So we need to make them into the metal ourselves by processing. So we're going to look at lithium and sodium for group 1. And these are industrially produced by the electrolysis of molten chlorides. So we've got a diagram taken from the book here of the sodium example, and it's done in a down cell. But if you want a video so you can see it in 3D and it cuts away and all the animations and stuff, it looks like quite an old one actually, but there's a YouTube video here showing how the down cell works. And essentially you take sodium chloride, of which there is loads in the sea, it's just salt, and it actually has a bit of calcium chloride in there as well. This is just to lower the melting temperature, it's not for any other chemical reason. So a molten solution of sodium chloride is put in this electrochemical cell, and a current is flown between the anode and the cathode. And at the anode, chlorine ends up getting oxidized. So the definition of oxidation is that oxidation is a loss of electrons. So you can see the chloride anion gets oxidized to molecular chlorine, Cl2, and leaves us a gas. And then at the cathode, these electrons reduce the Na+, the sodium cation, into molten sodium metal, and as this is less dense than sodium chloride melt, it starts floating and it leaves through this through this tube. And down here we show how potassium, rubidium and cesium can be formed, and this is similarly by melting the chloride salts. However, it's now a displacement reaction, so you'll start with a potassium chloride molten, and mixed with liquid sodium, and then the chlorine jumps from the sodium, from the potassium to the sodium, leaving you with purified liquid potassium. So for the alkaline earth metals, we're going to be mainly looking at magnesium, and calcium on the next page as well. So magnesium and calcium are the most abundant and most importantly commercially important metals in group 2. Both of these are in the top 10 most abundant metals elements in the Earth's crust as well, so there are a lot of them. The magnesium we obtain from seawater, so Mg2+ is the second most abundant cation, and this is going to be after sodium, from the sodium chloride. But it's got a couple of steps first. So first we react the magnesium 2+ cation with calcium hydroxide, and this is a displacement reaction where then the magnesium gets the hydroxides and the calcium is just a calcium 2+ cation. This will then precipitate out because it's not soluble in aqueous solution. This solid magnesium hydroxide precipitate is then treated with hydrochloric acid to make magnesium chloride. And then finally, we use electrolysis like last time. We melt the magnesium chloride, put it in an electrolytic cell, and the metal gets reduced at the cathode to make liquefied metal, and the chlorine again gets oxidized at the anode to produce chlorine gas, which then leaves the cell. So we can also get these metals through the natural minerals that contain them. So some examples of magnesium containing minerals are magnesite and dolomite. And if we take the example of dolomite, there's a two-step process to producing magnesium from it. So it's a mixture of magnesium carbonate and calcium carbonate. And in the first step, you heat it very high and the carbonates decompose, you lose CO2 and end up forming a magnesium oxide, calcium oxide solid mineral. And then this gets reacted with an iron silicon alloy, which is called ferrosilicon. And this occurs at a very high temperature, at 1200 degrees. Let me make a note of that there. And under these conditions, this ferrosilicon reduces the magnesium oxide to metallic magnesium, but 1200 degrees is over the boiling point of magnesium, so this just leaves as a purified magnesium gas, which can then be collected and refined into solid magnesium. There's a similar thing occurs with calcium, so it's also in a lot of minerals like limestone, apatite, gypsum. If you ever go to Britain by boat, you'll come across the White Cliffs of Dover on the way in. Some very white cliffs, not very creatively named, and this is because they have a lot of limestone and calcium in them from the bodies of dead sea creatures from long ago. And this is done in a very similar way. So it's the reduction of calcium oxide. This can be formed in a similar way by taking calcium carbonate or limestone, heating it to around 1000 degrees, and the carbonate will decompose and you'll end up with the calcium oxide. And then this is reacted again at very high temperatures with aluminium, and the same thing happens. The calcium oxide gets reduced and you end up with metallic calcium above its boiling temperature, so it leaves as gas to be collected. Finally, let's look at the uses of some of these metals after we've made them. So sodium is far and away the most important. Lithium is also used a lot, especially in the sort of the modern day when everything's got a battery in it. I mean, the Teslas, the cars have batteries, the phones have batteries, the laptop have batteries, and most of these are lithium-ion batteries. So a lot of the lithium isn't used. Sodium, though, is table salt, so that doesn't even require much processing. Herbicides and washing sodas as well. Bleaches contain a lot of sodium compounds. However, the production of sodium metal itself has fallen by 80% since the 70s, and this is due to the banning of lead in petrol. So when petrol was first used, tetraethyl lead was added as what's called an anti-knock agent. So it just made the engines run a bit smoother. It's been banned because lead's quite unhealthy. But in the production of this triethyl lead, sodium metal was used. And since we don't need it anymore, sodium metal isn't used so much either. Now the group 2 alkali earth metals are used in a fair few things. Magnesium is in a lot of enzymes. They're also present a lot in the natural world. So this is magnesium's in chlorophyll as well, which we'll see in one of the following slides. Calcium's present naturally as limescale, as we were talking about, used a lot in cement and building, and also in spectroscopy. In the lab we use calcium fluoride because they're what we call optically transparent. So this doesn't just mean optically by your eyes we can see through glass and that's transparent. But if you try and do things like infrared spectroscopy or UV spectroscopy, conventional glass can interact with the infrared and the UV, can absorb it and mess up your measurements. Whereas calcium fluoride, even in the UV and the IR, is transparent, so that's nice. Strontium is used in pyrotechnics, so fireworks, and yeah, colour TV tubes. This is clearly a bit outdated because no one has tube TVs anymore. And barium is used a lot in medicine for X-ray tracking. So it's yeah, it absorbs X-rays a lot. I believe I have a picture here. Yeah, so you can see going down someone's esophagus here. They'll take a bit of barium, and yeah, you can see them swallow it, and it's very black because it's absorbing a lot of X-rays. And finally, the ones I was saying that have a lot of natural uses, the most common are magnesium and calcium. So magnesium is essential for plants and animals, and I've got an example when we come to a complex chemistry in the D block of a magnesium complex. But it's also in chlorophyll, so if there isn't enough magnesium, you get this kind of lime green, almost yellow colour. If you've got enough magnesium, the chlorophyll is all good and it's nicely green. And calcium's used a lot in mammals. It makes up our bones and teeth, but also, as I was saying, in the marine creatures that make up the limestone cliffs, like shells and things of crustaceans have a lot of calcium in them as well.